All right, this is a video for Algebra 2 on adding and subtracting rational expressions, and we're going to start with an introduction and then do a few solved examples. So we will be doing a couple reminders here relating to fractions and adding fractions, so a little bit of a flashback to what you've been doing maybe for years, but you might not have seen for a while. So, but before we do all that, let's do a quick reminder about what least common multiples are. So the least common multiple of two numbers is the smallest number that each of your given two numbers evenly divides into. Okay, so for example, the least common multiple of 5 and 6, what's the smallest number that both 5 and 6 evenly go into? It's going to be 30. But it won't always be simply the product of those two numbers. Let's think about the least common multiple of 10 and 6. Okay, 10 times 6 is 60, so 60 is a multiple of 10 and 6. But there's a smaller number, 30, which would be the least common multiple of 10 and 6. And the strategy that I use to find these LCMs, as I call them, is to do some prime factorization first. So let's turn 18 into its prime factorization. It's 2 times 3 times 3. And let's turn 30 into its prime factorization. It's 2 times 3 times 5. So I want you to think of primes as the building blocks of numbers, and we need to build a new number that has all of the components of 18 and 30 as part of that new number. So I need a 2 in my new one, so I need a 2. So my new LCM will have a 2 in it. It looks like I need 2 3s, and that's going to take that 3 off the table. We won't need that one anymore. So we need 2 3s because 18 has 2 3s. And then we need a 5 as well. Okay, so I grab the minimum number of prime factors I need to make sure that each of my original given numbers are represented. And you could think of it also like this. 18 is represented by this 2 times 3 times 3. And 30 is represented by this 2 times 3 times 5. So each number is represented in my LCM that I'm building. And then we just need to do that multiplication. What is 2 times 3 times 3 times 5? I could probably do it in my head, but I won't. And I get 90. So my LCM is 90 here. We can do something similar with algebraic expressions as well. We just still need to do the prime factorization and then grab the minimum needed to build each of the two given expressions we start with. Okay, so let's do a prime factorization of 14x squared y. It's 2 times 7 times x times y. And 10xy cubed is 2 times 5 times x times a product of 3y's. Okay. So it looks like I need a 2. It looks like I need a 7. It looks like, well, here's another strategy I'll follow. Let's just rewrite the original prime factorization of one of the numbers that we started with. And then let's see if we have everything else represented. So we have a 2. We don't have a 5, so let's multiply by 5. And so now we have this 5 represented. We have an x represented. We have one y represented, but we need 2 more y's represented to build the 10xy cubed. And then we can just simplify this. We get a 2 times 7 times 5, which is 140. Nope, 70. And then we have x squared right there. And we have the product of 3y's, so y cubed. So that's the smallest, the lowest expression that is a common multiple of each of our two given terms. Let's get a little bit more complex even here. And so you can see that sometimes we can do some factoring as well. So I am going to write this first expression as 2 times 2 times 3. I'm just going to keep my variables as in exponential form. But then I can factor some of these trinomials I've been given. 18 is 2 times 3 times 3. We have an xy cubed, and it looks like we have an x plus 4 and x plus 1. So again, one way to do this might be to let's just bring down that we know we need all of those terms. And then let's see what's not included. We have a 2, we have a 3, we need another 3, we have an x, we have one y, but we need a y cubed, so I'm going to throw in a y squared here. Okay, we need an x plus 4, and we already have an x plus 1. Okay, so I'm not going to do the full multiplication here, but I will do some of it here. This 2 times 2 is 4, 3 times 3 is 9. Looks like we have an x squared, we have a y cubed, and then we have x plus 1 quantity squared, x plus 4. And I can just turn that 4 times 9 over here into a 36. So again, the whole point here is to build probably a larger term, doesn't have to be larger, but it usually is, that each of our given terms evenly divide into. So if I were to do some division, which I haven't taught you how to do some of this complex division yet, but if I were to do some division here, each of our given terms would evenly go into our final answer. And so that was just a reminder of least common multiples, and then a little bit of some challenge work with that as well. Let's do a reminder of adding fractions. And the reason we work with least common multiples is we need to think about what the least common multiple is of our two denominators, because we need to get common denominators. So least common multiple of 2 and 3 is 6. So I want to build a 6 right there. I want that to be a 6. So I can multiply top and bottom by 3 over 3 here and by 2 over 2 here. That's an allowable thing to do because I'm multiplying by 1. It doesn't change my variable. It doesn't change my number I'm working with. 3 over 3 is 1. I'm allowed to do that. So let's go ahead and multiply our fractions. This turns into 3 over 6 plus 2 times 7 is 14. 2 times 3 is 6. We have common denominators. We can go ahead and add them now. 3 plus 14 is 17 over 6. Final answer right there. Okay. Let's do another example. 15 and 10. What's the least common multiple of 15 and 10? It's going to be 30. How do we build a 30? Well, we need a 2 over 2 here, and we need a 3 over 3 here. Okay. And when I do my multiplication, again, I'm multiplying straight across the top to get a 26, straight across the bottom to get a 30, and then plus 27 over 30. I have a common denominators. My final answer will not have a denominator of 60. We keep that denominator, and 26 plus 27 is 53. And then I can think about if I could reduce that at all, and that is, I don't believe that's reducible. Okay. Your teacher might want you to write it in mixed form, which is fine. It would be 1 and 23/30ths. But if you don't have any instructions to do so, it's fine to keep it as an improper fraction. So adding rational expressions, just the same as adding numbers. Okay, we need to get a common denominator using our understanding of least common multiples and common denominators, and then we just go ahead and add the numerators together. So let's factor the right-hand numerator first. So I'll rewrite my equation or my expression here with that factored. And that's going to be x squared. We have a couple x's here, minus 2 and minus 1. Okay? So let's build a least common multiple. In other words, build a common denominator from those two terms, those two expressions. And I hope you can see that if we multiply the top and bottom of my initial expression, my first fraction, by x minus 2 over x minus 2, now that denominator is the same as that denominator, and we'll be able to add the fractions together. Okay, so let's be careful with the distributive property here. We have x times x and x times x minus 2, and I'm just going to not try to do too much at once here. I'm going to write down my work. So x times x minus 2 over x minus 2 times x minus 1 plus 2x minus 1 over x minus 2 times x minus 1. We have common denominators. Let's get them into one simple fraction, and I'll do that distributive property now. And I'm not going to multiply the denominator at this point because I'm thinking ahead. I'm thinking, maybe there's a situation. I made a mistake in my denominator. Let me fix it. Maybe there's a situation where I might be able to do some canceling along down the road, and I'm thinking that might happen. So again, just to be clear, this turned into that, and this was brought down here like that. And let's move up here. We can simplify. We have an x squared minus 1 up top, and we have an x minus 2, x minus 1 down below. And I can factor that numerator now. That's a difference of two squares, x plus 1, x minus 1, over x minus 2, x minus 1. So we do have some nice canceling that can happen here. And my final answer here is going to be x plus 1 over x minus 2. And I need to keep in mind, what can x not be? X cannot be a 2. But what else can x not be? Looking all the way back in my work, it looks like x can also not be a 1 because of that term right there, which got canceled out. But I always like to scan through all my denominators throughout my whole sequence of work to see what my limitations might be for x. So there's my sum right there of those two fractions. And we'll do a couple more examples here. Subtraction, virtually identical to adding. We just need to make sure we're dealing with the minus sign appropriately. So I will factor the numerators, the denominators here. That first one has a GCF, x gets pulled out. The second one looks like it has a GCF of 2. We have an x minus 2. So I need to get some common denominators here, and I need a 2 to show up in that denominator because of that 2 right there. So I need a 2 in that term also. And I need an x to show up in this denominator because of that x right there. I need an x in that denominator also. And we already have an x minus 2, so that's all set. We don't need to worry about anything there. So let's do my multiplication, and I'll do the distributive property all in one step as well. So, whoops. 2 times, let's do the distributive property. 2x plus 4 over 2x, x minus 2 minus x squared plus 2x over 2x, x minus 2. Okay, so we have some more work to do here. We have specifically the subtraction. I think the thing to keep in mind is this subtraction applies to that term and also to that term. So we're subtracting both terms here. So this, let's get it into one fraction, and I'll do it up here. 2x plus 4 up top, minus an x squared, and then minus a 2x as well, all over my common denominator of 2x, x minus 2. So let's simplify. We have a negative x squared up top. Look at this, our x's cancel, our 2x's cancel. And we have a plus 4 as well. This is going to be an interesting result here. It'll be kind of cool. And we have a 2x times x minus 2. What this up top makes me think of is a difference of two squares. We could rewrite it as 4 minus x squared. But what I think I want to do to connect with something that we did earlier is factor out a negative 1. So I'm going to rewrite this as follows. And then I think you can see that maybe we'll be able to cancel that x minus 2 in the denominator. So we can keep going with it. We can do the difference of two squares, factoring. We have a 2x and an x minus 2 down below. And then we can do some canceling, which is nice. So up top, it looks like our final answer will be a negative 1 times x plus 2 all over 2x. Okay. Now we just need to think about what x cannot be. Okay, we're not allowed to have zeros in denominators. So x can't be 0, and that's because of this term right there. X can also not be 2 because of that term right there. And let's scan back through everything else. You really don't need to look at the original as long as you're looking at the factored forms, and I think that's easiest to do, look at the factored forms. So it looks like we've captured everything that x cannot be, so this would be our final answer right there. Okay, so we subtracted those two fractions, and then we were careful to write down what x cannot be. We're going to do one more example here, I think, yep. Look at some complex fractions and try to simplify this guy a little bit. So complex fractions are essentially fractions of fractions, and I think you would agree that this one does look complex for sure. Same rule applies. We can always multiply any piece of any expression by 1 or a special version of 1 without changing the value, but we want to be strategic and make sure we're creating common denominators as we're doing this. So let's multiply this fraction up here by y over y, and this fraction down below over on the right by x over x. Okay, and let's realize that this 1 right there is equal to 1 over 1, right? And so we can multiply the top and bottom of that fraction by y over y to get common denominators. So we're going to have two separate common denominators. Common denominators up top of x times y, and a common denominator down below of just y. And then we'll do some work after that to do the overall division, but we're just working separately in the top and the bottom of this fraction. So we have a y over yx plus x squared over yx up top, and down below we have a 1 over y plus y over y. Okay, so we have some common denominators. We can do the addition in the numerator, we can do the addition in the denominator, and we can move forward. So we get a y plus x squared over xy. I like putting things in alphabetical order. And we have a y over y squared. Okay, so let's see what we can do now. We're doing a division of two fractions, so we can invert the second fraction and multiply. And I'll bring it down below. So we have a y plus x squared over xy times the inversion of that denominator, y squared over y. Made a mistake, right? Hope you're seeing that. I made this very common mistake of turning that into a y squared. So hopefully you're seeing that mistake, and I think that's my only mistake, so let me fix that. Hopefully maybe you've been telling the screen, Alex, you made a mistake for a little bit now. So let me fix that. So that is just 1. Wow, that's a big mistake on the bottom. I'm going to start over, and just remember that it's okay that we make mistakes. We want to try to learn from them and fix them. So I think the numerator of my fraction is fine. It's my denominator that was pretty far off. So this was 1 plus y over y. Wow, that was a big mistake I made, but it's no problem now. So now we can invert the second fraction and multiply. So this is going to turn into y plus x squared over xy times y over 1 plus y. And I think you can see we have some y's that can cancel out, and we end up with y times y plus x squared all over x times 1 plus y. Okay, I think that mistake came from I'm mixing adding, where we keep the same denominator, and multiplying, where we multiply the denominators. And so that's a really important message to take home here. In this case here, I was adding, and so that's why I needed to keep the same denominator. In this case here, I'm multiplying, so that's why I multiplied the denominators. Very easy mistake to make. Okay, let's see if we can do any simplifying. I don't think we can though. So we could go ahead and do the distributive property, y squared up top plus x squared y all over x plus xy. So that would be a reasonable final answer, although we would want to keep in mind there are plenty of places along the way where x and y were in the denominators, so we want x and y to both not be 0. And that would be our final answer right there, and that is a good place to stop.